Right, so continuing our conversations about triangles, we're going to talk starting about perpendicular bisectors of segments. A perpendicular bisector is a line, segment, or ray that passes through the midpoint of a segment. What do midpoints do? They divide a segment directly in half. So this midpoint cuts the segment in half. And it is perpendicular to that segment. Perpendicular means what again? What does perpendicular mean? Yep, means it forms a right angle. So a 90-degree angle. So when we talk about a perpendicular bisector, it cuts the segment in half and it makes a right angle. So we've got a picture of one down here at the bottom of my screen. This would be a perpendicular bisector because you'll notice it is forming two congruent segments on either side. And there's a right angle here, so point D would be a midpoint. And our perpendicular bisectors have an interesting feature, an interesting characteristic. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Equidistant means same distance. So you'll see this point C is the same distance away from A that it is from B. If we put in another point on this line segment, like if I put a point E up here, this point E would be the same distance away from A that it is from B, because it is on the perpendicular bisector. And that's true even if we get closer to the segment. So if I put a point F down here, this point F would be the same distance away from E that it is from B. If there is a point on the perpendicular bisector, then it is equidistant from the two endpoints of the segment that the perpendicular bisector is bisecting. So if I know I have a perpendicular bisector, I can show that it is equidistant from the two endpoints. And then we have the converse of that. If I know that I have a point that is equidistant from the endpoints of a segment, then that point is on the perpendicular bisector of the segment. So let's see if we can apply the perpendicular bisector theorem and its converse. Let's look at example number 1 here. What do you notice about EG and GH? Yep, they are congruent sized segments, which means G would have to be what? If on either side of it we have congruent segments. What do we call that special point there? The midpoint. G is the midpoint. And what do you notice about the angle that EH and GF are making? It's a right angle. So that means that GF is the perpendicular bisector of EH. We have that EG is equal to GH, and the measure of angle EGF is 90 degrees. So we have a midpoint and we have a right angle. So that means that GF is the perpendicular bisector of EH. So now let's see if we can take and apply that idea, because we know that GF is the perpendicular bisector. What does that mean about the lengths of EF and HF? They are congruent, yes. F is on that perpendicular bisector, so EF and HF are congruent. So that means the length of EF equals the length of HF. How big is segment EF? 4A minus 15. And what about HF? A plus 12. We're going to solve this for A so that then we can use that to find the length of segment EF. So I'm going to get my A's to the same side. We're going to subtract A from both sides. 4A minus A would give me 3A. We're subtracting. Minus, yep. So 3A minus 15 equals 12. Then we're going to make the 15 cancel out by adding 15 to both sides. 3A equals 27. Then we divide both sides by 3, and A equals 9, yes. But what did they ask me to find in the problem? It says find EF. Well, what did we say was the size of EF? What's in the picture? 4A minus 15. And we just figured out that A is 9, so I have 4 times 9 minus 15. What is 4 times 9? 36. And 36 minus 15? 21. So EF is 21. Nicely done. Let's see if we can try another one like this. Let's look down at number 2. What do you notice from the picture? What's already marked for us? QS and ST are congruent. QS equals ST. Anything else that's marked in the picture? The right angle. Angle RST is 90 degrees. So that means that point S would be a what? That'd be a midpoint. And because SR is going through that midpoint and making a right angle with QT, that means that SR is the perpendicular bisector of QT. Because SR is the perpendicular bisector of QT, what do we know about QR and TR? They're congruent. QR is congruent to TR. So that means the length of QR is equal to the length of TR. What is the length of QR? Two x plus 3. And TR? 4x minus 7. Let's solve this for x so that then we can use that to find RT. So I'm going to get my x's to the same side first. So I'm going to minus 2x from both sides. That would give me 3 equals what? 3 equals 2x minus 7. Then we want to make that negative 7 cancel out, so I'm going to have to add 7 to both sides to get my constants over on the left. I get 10 equals 2x. And then we divide both sides by 2. So x is 5. But that is not what I was supposed to find. What did they ask me to find here? They asked me to find RT or TR. And RT was 4x minus 7. So we do 4 times the x that we just found, which is 5, minus 7. What is 4 times 5? 20. And 20 minus 7? 13. So RT is 13. Nicely done. Let's flip over to page 4. We are going to use the converse of the perpendicular bisector theorem to find some segment lengths here. What do you notice in the picture for part A? There's 2 things that stand out to me here. What's one of the things you notice? WY. WYX, that angle, is a right angle, yes. We have a 90-degree angle right here. The measurement of angle WYX is 90 degrees. It's not an angle bisector necessarily. It might be, I'm not sure. I don't know that it's an angle bisector. How do you know? How do you know from what's in the picture? It's not a perpendicular bisector just because it's perpendicular. It is perpendicular though. Because of the right angle, that means it's perpendicular, but that does not mean it's a bisector. What is it that tips us off to it being a bisector?
WZ is congruent to WX.
WZ 25.3 is congruent to WX 25.3. WZ, well, without that information, you don't know that it's a bisector. You know it's perpendicular, but you don't know the bisector part. WZ is congruent to WX. So that means that WY is the perpendicular bisector of XZ. If WY is the perpendicular bisector of XZ, then how big is XY? 22.4. This segment here would be congruent to this segment here. XY is congruent to YZ. So XY equals 22.4. Part B, it says that we're supposed to find WY. How big is WY? That I have circled over there on part B. I don't think you're looking at the right part, sweetie. Part B. Over there.
3.
3. How do we know? It's congruent to YZ. And how do we know that it's congruent to YZ? Yes. And there's one more piece. And how do you know that XY is the perpendicular bisector? That's not the only thing. That's the bisector part. There's one more piece.
XY is perpendicular to WZ.
XY is perpendicular to WZ. There's two pieces that have to be true for it to be a perpendicular bisector. You have to have the right angle, and you have to have the two segments that are congruent, 9 and 9. Right. That's how we know it's a perpendicular bisector. If all you see is the right angle, then you know it's perpendicular but not a bisector. When you see the two congruent segments, you know it's a bisector, but you don't know it's perpendicular. You have to have both of those pieces together for it to be a perpendicular bisector. All right. So we're going to write our definition for a perpendicular bisector here. This is a segment line array. That splits another segment into two congruent parts. At a right angle. So we're going to draw a perpendicular bisector here. Perpendicular bisector cuts my segment into two congruent parts, and it makes a right angle with that segment. Any point that is on that perpendicular bisector, like if I name a point right here, let's call this point C. That point is equidistant from my two endpoints. So when we have points on the perpendicular bisector, and we draw segments from a point on the perpendicular bisector to the end points of the segment that's being split, we basically turn this into an isosceles triangle, into a triangle that has two congruent sides. So let's write a couple true statements or equations or properties about the perpendicular bisector. We already said that segment AC is congruent to segment BC. If the segments are true, then what would have to be true about their measurements? Same size. So the length of segment AC would be equal to the length of segment BC. Are there any other segments up there that are the same size? Ooh, good point. What should we call this one, do you think?
Y.
You want to call it Y? We can call it whatever we want to. So then what segments would be congruent? AY and BY would be congruent. If they're congruent, then what's true about their measurements? They are the same. They are equal measurements. What's the relationship between AY, where Y is my midpoint, and AB? What's the relationship between this segment and this segment? AY is half of AB. So if I wanted the length of AB, but I only knew the length of AY, what could I do to the length of AY to find out the length of the whole thing? Multiply it by 2. So I could do 2 times AY to get AB, yes. There's something else that's marked in the picture that we could say. We put the marking on the picture, but we haven't made a statement about it. The perpendicular part. What angle is making a right angle? CYB. Measurement of angle CYB is 90 degrees. Are there any other 90-degree angles up there? CYA. Measurement of angle CYA is also 90 degrees. Because we have a right triangle, we've got this little guy that's a right triangle, and then the other side is also a right triangle. What do we call the side of a triangle that's across from the right angle? The hypotenuse. Has anybody ever heard of the Pythagorean theorem? Pythagorean theorem helps us find missing sides in right triangles. The Pythagorean theorem says that I take the two sides that are not the hypotenuse, so CY and YB, and we square them and then add them together. So I can take CY and square it, I can take YB and square it, and that equals the length of the hypotenuse, CB, squared. There's my Pythagorean theorem. I could do that about the other side too. I could say that CY squared plus AY squared equals CA squared. Anytime I have a right triangle, I can take the two sides that are not the hypotenuse, the two sides that are not opposite the right angle, square them and add them together, and that will give me the length of the hypotenuse squared. Let's see if we can use some of these ideas to help us with problem number 6. And then we're going to shut it down for today so that I can have a chance to pass back your tests to you guys so you can see how you did on those from last week. So let's look at the picture here in number 6. Name the perpendicular bisector and the segment it bisects. So which segment is the perpendicular bisector here? Which one is the one doing the cutting? BD. So BD is the perpendicular bisector. It bisects which segment? AC. So that means that D would be what? What would we call that point? That's the midpoint. If BD is a midpoint, and if D is the midpoint and BD is the perpendicular bisector, then that means that AB and is congruent to BC. So BC is how big? BC is 11. D is the midpoint and DC is 9. So how big is AD? 9. Well, if AD is 9 and DC is 9, how big is AC? 18. 9 plus 9 gives us 18 for AC. There is one more piece they want me to find. They want me to find the length of BD. In order to do that, I have to look at this right here as a right triangle. We've got our right angle down here in the corner. Which side would be the hypotenuse? Which side is opposite the right angle? BC right here. This is my hypotenuse. So that means that if I do A squared plus B squared equals C squared, this is my Pythagorean theorem. The two sides that are not the hypotenuse are DC, so DC squared, and BD, so BD squared, equals my hypotenuse. What's the hypotenuse again? BC, so BC squared. Let's start substituting in some numbers here. How big is DC? 9. So I have 9 squared. Do we know how big BD is? BD. Not yet. But we do know how big BC is. BC is how big? 11. So I have 9 squared plus BD squared equals 11 squared. What is 9 squared? 81. So 81 plus BD squared equals, what's 11 squared? 121. I want to get BD all by itself, so I'm going to subtract 81 from both sides. So I have BD squared equals, what's 121 minus 81? 40. And then we square root. We want to get rid of this squared right here, so we have to take a square root. And if you do it to one side, got to do it to the other side. Now, when we take a square root, we end up with two possible answers. We end up with a positive answer or a negative answer. So BD is equal to plus or minus the square root of 40. What is the square root of 40 in decimal form? Grab a calculator if you need to. Let's take it out to 2 decimal places. 6 point.
3, 2,
6.325. And now my last question here, because anytime we take a square root, we get two answers. But BD is this segment right here. Could you go and measure a segment with a ruler and get a negative length? No. So the true length of segment BD would just be the positive 6.325. We get two answers from doing the square root, but only the positive answer makes sense here. All right. That is where we're going to stop for today. The homework that you guys picked up on your way in the door is due on Thursday. Homework is due on Thursday.